So today, as much as I'd love to present some of my own work, I thought that maybe it would also be more valuable for the group if I just kind of review the basics of Hamiltonian Monte Carlo. That way, I mean, it's such a prevalent tool for high dimensional Bayesian inference that it's kind of a shame not to spend at least a little bit of time talking about it. So let me go to full screen. There we go. And I need to do a new share. Okay, so everybody sees my slides. And then if I go to the next one, do we see that too? Okay, great. Okay, so Hamiltonian Monte Carlo is an MCMC algorithm that is extremely useful for learning posterior distributions for high dimensional models, and that's really where it has its strength, is with high dimensional models. Just a brief recap. I know that all of you are familiar, but let's talk about Bayesian inference. And here I'm going to simplify things, and I'm just going to say that my data is IID and that I've put a prior on some parameter theta, some model parameter. And then the usual terminology, the probability of all my data conditioned on that parameter is my likelihood. And then again, P of theta is my prior. And then the goal of Bayesian inference is to learn the posterior distribution of theta. And we usually do this thing when we give these Bayesian statistics talks, where we say something like, we're interested in the left-hand side in the distribution of theta conditioned on our data. But then look at this denominator. That involves this integral. And in most situations, this integral it's intractable. So instead of, getting that posterior distribution directly, what we need to do is we need to actually perform MCMC. And this is fine. I guess it's kind of true, but the reality is that that's not the integral that we're interested in. We're interested in another integral. So what we're really interested in is for some arbitrary function f. Maybe it's an interesting function, maybe it's a simple function, I don't know. But we're interested in the expectation, the posterior expectation of that function f. That's the actual integral that we're interested in. I guess it's a minor point, but I'm just saying that this denominator is, even if we did know what the integration constant is, it wouldn't help us really that much for computing this integral. So anyway, we're statisticians, and what we do is we collect samples from our posterior instead of performing this integration. Because that's what statisticians have done from the beginning of the time, is we collect samples. And we can't go outside and we can't poll people and we can't, collect these samples from some large database. So the way that we collect these samples is we actually are going to generate them ourselves. And the bottom line is that once we have this sample, then we rely on some sort of law of large numbers, and that's going to allow us to actually get that posterior expectation. Yes, but where do we find our samples? The gold standard for posterior Bayesian inference is to actually generate a Markov chain. And Markov chains, they can be very useful for this difficult problem. But what they do is they actually iterate sequentially through time, and they generate new states of the Markov chain. And then somehow, as this Markov chain gets longer, then our marginal distribution, collapsing across time is going to look more and more like the target distribution. So here we have in the upper left-hand corner, we have a trace plot. This is just showing we're trying to sample from, I guess it's a standard normal distribution. And we're moving through time. And here we've done 1,000 iterations. And here are our samples. This is it. Then the next row, we have 1,000 samples. And it's starting to look a little bit more like our goal, which I'll only speak technically. This is called the furry caterpillar. We want our posterior distribution to look more and more like a furry caterpillar. That's all. And then you see that as we get to our third row, now we've done 10,000 iterations. So we've gone from 100 to 1,000 to 10,000 iterations. Our posterior trace plot is looking a little bit more like that furry caterpillar. And then accordingly, actually the histogram itself is, the empirical histogram is looking more and more like our target distribution. So that's Markov chain Monte Carlo. And we're gonna kind of assume, I'm gonna assume in this talk that you're more or less familiar with it. If not, then, you know, you can maybe draw a black box around some things, but maybe you can still get the gist. Actually, Markov chain Monte Carlo is what we're going to talk about today, but to actually go about things in a non-standard way, I'm gonna take a step back and I'm gonna just talk about a non-Markov chain Monte Carlo algorithm. So rejection sampling is kind of the basis for all of this. And I'm pretty sure it's John von Neumann that invented this. And his goal is to actually draw samples. Our goal is to draw samples from this distribution P of theta. So now I'm just ignoring any sort of dependence on the data. But we only know that distribution up to some constant. We can easily sample from another distribution Q of theta, and we actually know we know a number m. We have access to this number m that's greater than 0, such that m times Q of theta is what we call an envelope function for P star of theta. So it's always larger than P star of theta. So what we're going to do in this algorithm is we're going to generate so in each step of this algorithm, we're going to generate a draw theta from our target distribution. And the way that we're going to do that is we're going to draw some theta star from Q. And then we're also going to assume that we can draw a uniform number between 0 and 1. And then we're going to say that we've actually done what we want to do, that theta star is actually the theta that we're looking for, as long as U is less than P star theta star divided by M times Q of theta star. And then you can show that this actually gives us what we want. Any questions there? Because I'm gonna in the next slide, I'm gonna do something completely irrational. So I just want to make sure that all of us understand this. Okay, so the completely irrational thing that I'm gonna do is I'm going to do what I call the funky rejection sampler, which is something that that I'm very proud to say that I made up. And we have the same goal. We want to sample from some generic P of theta. And in this situation, we can. But we also feel the compulsion, the strange compulsion to use the invertible differentiable function T. So you can imagine that every time that we use this function, maybe somebody gives us $1, something like that. And of course, this is completely made up, but let's just assume that every time we use this function, somebody gives us $1. That's nice. So then this is my algorithm for generating a random variate from P of theta. I'm actually gonna draw, and again, this is the weird thing, but I actually can draw directly from P of theta, but I'm going to draw this theta cross or theta dagger. And I'm going to draw this uniform random number. And then I'm going to obtain my proposal theta star. And what it is it's this function T of theta dagger. Well, then I'm going to recognize that my proposal distribution, this Q from the last slide, is actually, well, we learned this in our probability 101 class. It's just P of the inverse transform of T. And then I need to add this Jacobian correction in here. So I'm taking also the determinant of the gradient of T inverse. And we've seen this before. And what we're going to do is we're going to do the exact same thing that we would do in any rejection sampler setting, is we're going to say that theta star is theta, that it's what we're looking for. If U is less than P of theta star divided by that denominator right there, which when we plug in our formula for Q, then it's just going to be P of theta star divided by M. Okay, M is there, that's fine. And then it's divided by P of theta dagger, our original draw from the distribution. And then we're multiplying by the determinant of the Jacobian again. So this is irrational. And I thank you for your patience in seeing this completely irrational thing. But there it is. There's this Jacobian correction here. And in fact, so for those of us that are familiar with Green's algorithm, the reversible jump MCMC algorithm, or at least maybe we've heard of it, then what that paper did in I think it was the mid-90s, is it kind of presented a way of thinking about the Metropolis-Hastings algorithm when we do use these deterministic transformations. And I'm going to keep on using this notation T. That's my deterministic transformation. So here, an MCMC algorithm, and now we're proceeding sequentially. So we assume that we have the state at time s-1, and now we want to generate state s. Then what we're going to do is we're going to actually assume that we have this. We're not going to assume, we're going to create an ancillary, or actually it's better to call it an auxiliary random variate psi. And we're going to sample it from some distribution conditioned on theta. And here I'm using the Markov chain, the Markov chain style of writing a conditional distribution as theta comma. So here, this is a distribution that is actually conditioned on theta. So we're moving from left to right. So we can draw some psi from a conditional distribution conditioned on theta, and we're going to draw U again. And then we're going to obtain our proposals, theta star and psi star, by actually applying some deterministic function to theta and psi. And then we're going to also calculate what is our acceptance ratio. And this is just going to be P of theta star times the joint distribution of well, it's actually more than the joint, times the conditional distribution of psi. So, and then psi star, and then divided by the original variables before the transformation was applied. But then you also see here that we have to scale our usual Metropolis-Hastings criterion by this determinant of the Jacobian, in just kind of a very similar manner to what I showed you with my completely unreasonable, irrational, funky rejection sampler. Except here it might actually have use. So anyway, we're going to accept, we're going to say that our next state, that our theta s is theta star, as long as U is less than that acceptance criterion, than that ratio. Okay, and this brings us to HMC, but maybe now is also a good place to stop, because I imagine that there could be questions now.
Is the last line a typo? Oh, the last line in black, it shouldn't be theta at s minus 1? Becomes theta of s?
Yes, that's a typo. So it should be else theta s gets theta s minus 1. Thank you. Oh, wait. Aha, up there, top line, I said that theta is theta s minus 1.
Very good. Very good. Sorry.
So no, it's totally fine. There's going to be more opportunities to find typos, by the way. So the main idea of HMC is then that we're going to let T, our deterministic transformation, that's actually going to be the evolution of a Hamiltonian system. So the correct statement of Hamiltonian Monte Carlo actually resides in Metropolis Hastings Green. Of course, it's taken us a long time to actually realize that. Okay, so
yes? Say that last statement again.
Yes.
It didn't sink in.
Okay, so the correct way of thinking about Hamiltonian Monte Carlo is as an instance of Metropolis Hastings Green. So it's an extension of Metropolis Hastings that incorporates some sort of deterministic transformation.
Thank you.
Thank you.
Are you going to talk about Hamiltonian system in a detail a little bit more?
Yes, I will.
Okay.
Andrew, so the T function has to be one to one, is that right? The one to one mapping.
So because we can calculate the gradient, we know that at least locally it should be invertible, right?
Yeah, I see.
At least locally.
Yeah, I'm just curious, you said originally the idea is from the green for RJ-MCMC. In that case, the dimension is changing.
Yeah.
How this mapping works across different dimensions?
So, okay, so I'm not an expert in this, but in this case, if we have, so usually I believe that algorithm allots like a total number of dimensions that you can have, right? So we have like 100 dimensions possible. Mm-hmm. So what that algorithm will do is, I believe that in that case, psi is a random variable that inhabits the complement of the number of dimensions that theta inhabits. So, so here, I think, so if theta is 10 dimensional, then psi will be 90 dimensional or something like that. And that's kind of how he went about doing that. And it's not clear to me how he came up with this idea, by the way. I don't understand. I don't know. It seems like he pulled it out of a hat. But yeah.
Gotcha. Yeah, thank you.
But here the size are different. So I think that, so please feel free to ask more questions, but now I'm gonna do a change of notation. So earlier, theta was our parameter of interest, and now we're gonna call it Q. Psi was our auxiliary parameter, and now we're calling it P. And then now we're, instead of thinking about the posterior distribution of theta, we just have this pi of Q. This is a nicer notation to use when talking about Hamiltonian Monte Carlo. So our target is pi now. So with Hamiltonian dynamics, we have some things that we want to define. The first one is that Q is the position of some sort of object or hockey puck or something like that in space. P is the momentum of that object. So it could be actually moving around. So Q could be changing if P is non-zero. M is a mass matrix. So it is positive definite and symmetric, yes. U is our potential energy. So this is, to get our potential energy, we're gonna take, and this might be giving it away a little bit, but we're gonna take the negative logarithm of our target distribution, or the PDF of our target distribution. K is our kinetic energy, which should be kind of looking like something Gaussian. And then our total energy is H. It's a function both of Q and P because it's the sum of our potential energy and our kinetic energy. So those are the terms that we're going to be using. And then importantly, this system is governed by by the Hamiltonian equations. And this says that, you know, the infinitesimal change of our position, well, that's just going to be our velocity, which is our inverse mass multiplied by our momentum. And then also our infinitesimal change in our momentum is actually given by the negative of our gradient with respect to Q, which is exactly the gradient of our log target distribution. And then finally, it's also useful to think about this function t, big T of little t. So that t, you should be seeing that big T and thinking, well, we've seen deterministic transformations earlier in this talk. So it's also useful to think about this function t, big T, that we know exists, right? Because of, you know, this old uniqueness and existence of the solution of ODEs. And this is just going to map from our 2D dimensional space to our 2D dimensional space, and it's just gonna move us from, say, Q naught P naught to actually QT PT. So it forward evolves the system. So those are the useful terms. I know it's a lot on one slide. But then given these, we can actually perform Hamiltonian Monte Carlo. Any questions? Okay.
So the
yes.
Sorry, the M is user specified, or it's the algorithm will come up some smart M? Yeah.
So the M is user specified, although I'm an advocate for actually learning that M. And I can talk about ways of doing that nearing the end. But typically it's the identity, actually. So some more review of Hamiltonian dynamics now that we have these terms. There's three characteristics about Hamiltonian dynamics that we really like and that are going to become useful. One is that it's reversible. So what this means is that actually, if I evolve the system for an amount of time, little t, well, then I can actually go back to where I started, right? This is the classical Newtonian physics, right? That whatever Einstein did seems to have shattered. So in terms of the big T, what this means is that it has an inverse. And then we also have volume preservation, which means that if we take the determinant of the Jacobian of t with respect to our position and our momentum, then that's actually going to be equal to 1. And I'm not going to actually show that directly. The cleanest way to show that is actually to invoke Liouville's theorem, which is essentially that if the divergence of a vector field is equal to 0, then we know that that vector field preserves volume. So I'm only going to show you that the divergence is 0. And then we're going to, based on that old theorem, we're going to actually know that the determinant of our Jacobian is equal to 1. So this is often written as, you know, the inner product of nabla with our vector dq of t, dp of t. And then what this is really, it's the summation of dqd applied to that element of the vector, and then dpd applied to that element of the vector. And then what we're going to do in this step, and then in the following steps, actually, is we're going to just use the way that the specific form of Hamilton's equations, which is that dq dt is actually equal to the gradient with respect to our energy h with respect to position d. So that's the dth coordinate of our position. And then what happens is because we can interchange our partial derivatives, this whole thing is going to be equal to 0. The gradient, the infinitesimal change in dp d dt is equal to negative gradient of h with respect to q of d. So that's why we're going to get this cancellation. So we are using the specific form that Hamilton's equations take. We do the exact same trick, or a very similar trick, with energy conservation, which is what we want to show is that the Hamiltonian function, that energy, that global energy, does not change with time. So in order to show that, what we're saying is that dH dt is equal to 0, and it's a two-stepper. We first use really the chain rule, which says that dH dt is equal to well, that's the gradient with respect to q, and then dq dt, and then the same thing with our momentum. And then again, we're just substituting the form that we know dq dt and dp dt take based on Hamilton's equations. And again, that becomes 0. So yes, we're reviewing Hamiltonian dynamics, but this is all that matters really, is that this function big T is reversible, or invertible rather, that it's volume preserving, and that if we advance according to T, we're not actually going to change energy. 3 things.
Sorry, can you flip back to the last slide? Just 1 second.
Yeah.
What does the energy correspond to in a statistical problem?
So I'm going to cover that actually once we're done reviewing Hamiltonian dynamics, but the hint is that we have this potential energy term, which is actually the negative logarithm of our target distribution.
Uh-huh.
And then we also have...
Yeah, from the next slide, the total energy H is not, it's stable, but the U part could be changing, right?
Exactly.
Yeah.
So this brings us to really our goal, which isn't to talk about physics, but to talk about Hamiltonian Monte Carlo, which is, going to allow us to actually perform MCMC with dimensional targets. And we're going to augment our parameter space. So now, again, I'm going to try to use the term parameter space to remind you that we're actually interested in a model. We're going to double the size of our parameter space. And we're gonna introduce an auxiliary Gaussian variable P. Actually, P doesn't have to be Gaussian. There are instances where we don't use a Gaussian, but usually P is Gaussian. And we're gonna construct it kind of following the usual, following the past two slides. We're gonna construct our total energy function H. And we're going to assume that P and our target random variable Q are independent. So that's by construction. We're assuming that we have independence. So the energy that we're going to use is just going to be the negative logarithm of the joint distribution of Q and P. And again, because of this independence that we're assuming and that we're constructing, this is going to separate into our potential energy, which is the negative log of our target distribution, and then a kinetic energy term. Because P is Gaussian, it's going to have this nice quadratic form. So we're going to use that, and then we're going to start at for each iteration, we're going to start at Q, which is our current state. So Q is actually Q of S minus 1. And then we're going to we're going to generate a new state of the Markov chain by forward integrating Hamilton's equations for time t. So how does this work? Well, first we're going to sample P naught. And we're going to sample it from a normal distribution with the mass matrix that we want. And then we're going to obtain QT, PT by simply forward integrating the system. So we're going to apply our deterministic function. And then that QT and PT, those are actually going to be our proposals. And so we're going to accept Q of t with probability. And here I'm using the caret as the minimum. So with probability, which is the minimum of 1, and then this ratio, which is just the Metropolis-Hastings-Green ratio. We have the target distribution, and then we have what I was calling Q back then, but this is just the distribution that we're sampling P from, or P naught from. And then we're multiplying by this Jacobian correction. But because of the volume preservation of Hamiltonian systems, we know that the determinant of our gradient is going to be equal to 1. So that's going to disappear. And we're just left with the joint PDF. The PDF of the joint distribution of QT and PT divided by the same for Q naught and P naught. So that's the algorithm. Now, if there's no questions, although feel free to ask a question.
Andrew, I have one question.
Yes.
So why is P naught sampled from Gaussian with covariance M, but in the kinetic energy, you have M inverse?
That is because I'm taking the negative log of a Gaussian, a centered Gaussian with covariance M. So what the PDF is always that exponentiation of 1 divided by 2, and then you have the quadratic term. So in the 1D case, we have the quadratic term, and then we're dividing by, usually we just denote it sigma squared, right? So that M needs to be inverted because M inverse is the precision matrix. M is the covariance matrix.
So Andrew, you might be covering this later, but I just want to, I wonder what does after using the HMC, I can summarize the acceptance rate. Sometimes that number is high, like 90%, 95%, sometimes low, like 68%. I wonder, what does that really mean? Is being high a good thing or being low a bad thing or not?
So I'll get there, but I think that we need to go to the next slide first because it's going to kind of get us in that direction. So I will answer that, okay?
Okay, yep.
So that's the ratio that we use to accept our proposal, QT. Now, all that I've done in this slide is I'm writing the exact same algorithm again. So I've just rewritten the algorithm so that we could get everything on one slide. And then I'm including this, but wait. Because when we look a little bit closer at this ratio, and we consider it as, you know, the exponentiation of the logarithm of the ratio, we do nothing to it, right? Then we can actually see that what we have is the exponentiation of the total energy of Q naught P naught minus the total energy of QT PT. But these two quantities don't change when we forward integrate the system. As this Hamiltonian system evolves, or another way of saying it is as we apply this function big T to our initial position and our initial momentum, as we apply this, our total energy in the system does not change. So we have Euler's number raised to 0, and that's going to give us 1. So my first answer to Shinkai is that is that we should always be accepting our proposal.
So when we are not, then or when the probability is low, then it suggests something is wrong?
No, so that's my first response to you.
Yeah, okay.
And then I'll tell you why this is wrong. Actually, why it's kind of a joke. It's because we don't actually know what T is. We don't know big T. So what we need to do is we need to approximate this Hamiltonian trajectory. And we're going to do that using numerical methods. And that's where we're going to get this variation in the energy functions. So there's actually this forward integration of ODEs is a very old, very established literature. It's probably more established as literature than the entirety of statistics, but it's gigantic. But what statisticians have kind of and people in, in related fields have decided is a very good integrator to use, is called the leapfrog method. And this approximates, well, the first thing I'll say is that this is very useful. The second thing is that it's a very simple approximation, and that we could use more complicated approximations. But what we end up doing is we use a simple approximation. And the way that this works is if we have the system at time t and we want to move it forward to time t plus epsilon, then what we do is we break it into multiple steps. And in the first step, we advance our momentum by a half step. And we do that by simply adding epsilon divided by 2, and then plus the direction that we're moving our momentum in, which is, again, this is just the gradient of the log. But now the log target distribution evaluated at q of t. So q is still at time t. And then we're going to advance our position q a full step. And we're going to do that by, again, we've got q of t, and then we're adding an entire epsilon. So this is not epsilon divided by 2. So epsilon times m inverse, p of t, but now p is advanced. Now we're using p of t plus epsilon divided by 2. So we're actually using that half step in our momentum to update q. And then finally, we're going to finish updating p. And we're going to do that using our current position for q. That's qt plus epsilon. So this algorithm is exactly affects the right balance between complexity and simplicity. So it gets the job done while maintaining some level of simplicity. Maybe as I say it to you, you might be saying, oh, what's going on here? But if you actually look at it for 3 minutes, then you'll understand it. And one of the reasons that we don't use higher order methods, if you are familiar with the discipline of, integration of ODEs or numerical integration of ODEs, one of the reasons that we don't is because we're going to be using an accept reject step anyway. But, it does work better than other methods that are also simple. So for example, if our goal is to start here at this point and then to follow the trajectory of our system, then Euler's method with the exact same step size is going to actually diverge from the path, the true path. Whereas the leapfrog method, so this is a modified Euler's method that does pretty well. The leapfrog method, for all of its simplicity, is actually going to manage to stay on the target path. But then the very cool thing is that because of certain properties of the leapfrog method, which I'm not going to go into, but which are very rich mathematically, we can actually increase the step size to a large degree, a non-trivial degree, and we're actually going to stay on the energy contour that we want to stay on. And I took this, I stole this image directly from Radford Neal's famous paper on HMC. So actually, the leapfrog integrator is reversible, and it's also volume preserving. So to see that it's volume preserving, we can just look at the Jacobian itself of our numerically obtained t. So one step, one half update of p. Well, the gradient of p with itself is going to be 0. The gradient of Q with respect to itself is 1 because Q isn't moving. The gradient of Q with respect to P is 0, again, because Q is not moving. The gradient of P with respect to Q, well, that's just the gradient of our update with respect to Q. So that's just our Hessian. And then the gradient of P with respect to itself is 1 again, because this is the update for P. It's just P of T. The same thing goes with Q. And then if you look at the form that they take, we think about their determinant, which is what we want in order to show that we have volume preservation, then that's just going to be the product of the diagonal elements, which is 1. But the real point here is that actually this Leapfrog integrator actually maintains some of the positive things that we want, but what it's going to lose is we're going to lose energy conservation. And this is a complete result of the fact that we are just numerically simulating. We're not simulating from the system exactly. And then globally, one can actually show, and it's not very difficult, you can show that, you know, if I do this kind of long range proposal, which I'm generating by just tacking on, iterating the Leapfrog, that Leapfrog iteration that I showed you, then the total error that we're going to get is actually on the order of epsilon squared. So if I limit the size of epsilon, then I can actually control the amount of error in my system. But yes, we are losing that conservation of the Hamiltonian. So here, again, I'm stealing an image from Neil. We've got the evolution of the position coordinates and the momentum coordinates. And then you can see that as the system evolves, that the actual energy function is going up and down, which is going to affect our acceptance rate. So the algorithm at the end of the day is that we're going to specify some t, that is our trajectory length. And this is going to be big L, which is the number of Leapfrog steps, times our epsilon, our step size. And it's going to proceed in the exact way as, you know, our idealized version of the algorithm, except now we're using this t hat, this numerical approximation to big T. And you know, it has parameters given by the step size, epsilon, and the number of Leapfrog iterations, big L. But then we have the same acceptance rate. And that's because the gradient with respect to t hat has determinant 1. So that's the algorithm. Questions? So there's a lot of machinery here, but there's also just the right amount of machinery. But we often need to do things in order to overcome certain challenges. And actually some of these challenges, maybe HMC isn't the right tool. So the first challenge is ill-conditioned target distributions. So here, you know, at any point, maybe that the largest eigenvalue of the Hessian is much larger than the smallest eigenvalue for the Hessian. So these kinds of situations are very difficult for HMC to handle. It does better than Random Walk Metropolis, but it's still difficult. So what you can do is is you can actually change what M you're using. So you can adapt your big mass matrix. You can adapt it to the problem at hand. So that is one thing that you can do that can help. It doesn't solve the problem, but it can help deal with ill-conditioned target distributions. And there's different ways of doing that, but I'll talk about that more later if that's okay. And then something that HMC is probably not good at is multimodal target distributions. There are some theoretical results that say that, you know, random walk metropolis is actually going to outperform HMC if your target distribution is multimodal. What I would respond to this challenge is, okay, that's a valid challenge. On the other hand, in high dimensions, typically you're not worried so much about multimodality. What your space looks like is just everywhere is a saddle point for your distribution. So that is at least something that people say in the machine learning literature. The other challenge is big data. The fact of the matter is that your likelihood, your log likelihood, which is part of your log posterior, is going to become much more computationally intensive as the size of your data set grows. And the same thing goes for the gradient with respect to the log likelihood. So that's a major challenge, is, you know, dealing with big data. But that's kind of, there's some tension going on between, you know, big P, or like the size of your model, and then big N, the size of your data set, because we want to have it all. And then finally, the algorithm is complicated enough where, you know, the average Bayesian might not want to implement it themselves. And then, you know, some of the things that we end up having to do in practice make it even harder to implement. So, some variations on the core algorithm. So another major challenge is just the development of fast, flexible, and user-friendly software. Some things that we do in practice. So if, you know, we're worried about some sort of near periodicity in our MCMC chain, then some things that we're going to do is we're going to jitter the number of steps. So this is, you know, let's say that I'm taking 20 steps on average. Well, then I might be adding or subtracting, or maybe I'm sampling the number of steps from a Poisson distribution with mean L, something like that, before every iteration of Hamiltonian Monte Carlo. Some other things that I might do is I could select an epsilon so that I'm actually accepting the majority of my proposals. And then I might increase, or actually what this would be is decreasing the number of leapfrog steps until I'm up closer to one of the prescribed acceptance rates. So again, we actually need to think about how we're gonna choose our tuning parameters. So that's another reason why people would prefer to not have to tune it themselves, or to code the algorithm themselves. And maybe they would prefer to just use software that somebody else created, if it's easy enough to use and effective enough. The other thing, so then once we've selected our epsilon, then we can maybe adapt our number of leapfrog steps. And then something that I do in practice for very difficult problems is I adapt my mass matrix as well. And there's a bunch of different methods that I could use for doing that. So I might just actually compute the Hessian of the log posterior every millionth iteration or something like that, and just use the mean that I calculate. Or maybe I'll just use the empirical covariance of my momenta following, you know, Hario et al. 2005, the classic adaptive metropolis algorithm. And then finally, something that we also do in practice is we think about ways of implementing HMC in a way that is handles the computational bottlenecks more efficiently. And you know, that would be something like mapping these core computations to a GPU or something like that.
So for the M, in principle, you want M to be close to the Hessian of the log posterior, or what? How do you adjust using posterior Hessian?
Yes. So I always need to remind myself this one, because I can't remember if it's the inverse of the Hessian that we want close to it or not.
Right.
Okay.
Yeah. Yeah. I'm asking because you know, in optimization, there is a whole literature of quasi-Newton,
yeah,
which is actually either way, if you want to approximate Hessian or approximate the inverse Hessian. So there are both quasi-Newton methods for doing that. Just use the gradient.
Yeah, there's so I think that this is so this is an area of research that has been at least explored a little bit, is, you know, how to tune this M in the correct way. So for example, there's a paper from, I think it's like 2013 maybe, or maybe earlier. It's a NIPS paper. I guess it was NIPS back then, so a NeurIPS paper. And what they do is they use LBFGS, if I got that right, to to get their M.
I see.
And they show that it works, but one thing that they did not do is prove that it worked. And the reason that you can't prove that it works is because it actually violates one of the core rules of adapting Markov chains.
Mm.
So the whole thing is that what we really want is that our adaptations that they diminish.
Mm.
And this is all from, you know, it's not my work. It's from, like, you know, work in the 2000s by Rosenthal and Roberts and all those people. But the idea is that, you know, as we adapt, we slowly want to be adapting less and less. So, you know, that method from that NIPS paper that uses LBFGS, you know, they don't have that diminishing adaptations.
Mm.
So this is just an example of kind of the kinds of pitfalls that can occur. I mean, they were still published, so I guess that's, you know, who cares if it's accurate?
So the point is, if you adapt M, it shouldn't be too dependent on the Q or something.
Yeah, exactly.
Is that the point? I see.
That's the point, yes.
Oh, okay.
So we want it to be at least depending less and less on Q. So that's why it's good to, like, take the average,
right,
of all of the Hessians, because then you know that you're getting that diminishing adaptations.
I wonder how big of a problem is considered a big problem for HMC. Is 10,000 parameters big?
No, 10,000 isn't big. Actually, the way that you need to think about it is not just in terms of the dimension of the target distribution. You need to think about the target distribution itself. So if I have an ill-conditioned target distribution, then actually a small number of dimensions is difficult. So I really think, though, that, you know, actually you could do this on your computer in R or Julia. You could just program a simple HMC and you could tune it so that it does really well on 100,000 dimensional normal distribution.
Mm-hmm.
But there's, you know, there's other things that you should actually take into account as well when you do that. So one thing that HMC does very well, provably. So sometimes what we want to do is we want to, when we talk about how efficient an algorithm is, then we want to talk about the convergence of the algorithm.
Mm-hmm.
So this is the convergence of, your empirical distribution that is generated by your algorithm to your target distribution. So this is usually like a total variation norm type thing. But one thing is that when we use that kind of math to talk about it, we know that HMC is very effective. Even in incredibly high dimensions, it's extremely effective when your target distribution is log concave.
Mm.
And, from the optimization literature, you can understand that pretty quickly, right? Like, you're using that gradient information to guide your trajectories. So that makes sense. So again, when we program this up and we're looking at a high dimensional Gaussian distribution, well, that's fine. If we want to actually sample from a high dimensional Laplacian distribution, I actually don't know if I've ever done that, but I assume that it would start to perform less well.
Hmm.
Actually, is the Laplacian? No, the Laplacian, it should also work, right? That's log concave. So what's an example like an alpha stable distribution? And that's not even ill conditioned. So yeah, so that's HMC. And then I can actually, we've gone over actually quite a bit. I've been trying to be more deliberate when I present and give time to so I'm sorry to go over.
Andrew, would you share your slides with the group?
Sure. Yes, sorry.
I had some interest in this, so I programmed a primitive version of it in Julia. I'm happy to share with people if they want to play with my code, which is probably more digestible than these massive softwares.
By the way, if we have time, then I can show a quick simulation.
Yes, I have time, but for people who want to leave, feel free. Yeah.
Yeah. Okay. So let me.
Are there general massive standard tools for this? I mean, like.
In Julia, Xingkai is using a package called Dynamic HMC. It looks very decent. I think what Andrew is talking about is the first 3 bullet points, like jitter, error, and so on. That software in the beginning, they spend some time trying to do dynamically choose a good combination of error and epsilon. That package is very, I feel it's good, but I don't know.
Whistles make it hard to write your own software, though.
That's correct. We are just using this as a black box. Yeah.
Yeah, I was thinking about including a section if I ever revise my algorithms book.
Yeah, you should. Yeah.
And I would appreciate if Andrew or Wah, whoever, I'll pass it around, would critique it. It's written for clarity, not for speed.
By the way, Andrew, who invented this thing, HMC?
So I was born in 1987, and that's when the paper was published.
Who was the author?
So this is Duane et al. But I think that for me, the most famous name there is probably Anthony Kennedy. Is a pretty big name in the physics and MCMC literature. He was on it. Another one is so I can forward that paper though. But that is actually, why don't I just include it right now? Well, so if you, So so Duncan Roweth is actually another one of the big names, I think, on that paper. I'm gonna just forward this right now. And the language is actually very difficult. I mean, I'm pretty sure that I don't understand it. Sorry, my daughter is screaming right now. So this is, if anybody cares to check that out. So this is written in a different language than what we're used to. I'll speak for myself and what I'm used to. But I think that the big breakthrough in the statistics literature came with the 2011 paper by Radford Neal's MCMC from Hamiltonian Dynamics. I think that I really do think that that's enough. That paper is enough in terms of, contributions that actually allow us to understand this. So I think it's a non-negligible contribution, even though it's written like a review paper.
So it took more than 20 years to filter from physics over to statistics.
I mean, don't get me wrong. Neal and some others were using HMC, and this is some others in the machine learning community were actually aware of HMC and were using it. But yes, it took a long time for it to really reach its full impact. And so, I mean, it makes sense though, when you actually look at the original paper, it's not easy for me to understand. Again, I'll speak for myself. But it's crazy though. But it's crazy that it took that long, especially when when you write your dissertation about related algorithms and you've spent 5 years thinking about it. It becomes remarkably simple. I mean, when you devote your life to this stuff.
If you have a canned simulation, I'd love to see it.
Okay, sure. Okay, so I'm using R. And then this is kind of, again, Shinkai, this is a Gaussian target. So this is kind of it at its best. And our target distribution, this is just the log of our target. The gradient, and I'm comparing to Metropolis Hastings. And then I've got this HMC, which is extremely simple, a very simple implementation. I'm not even jittering or anything like that. I don't think I'm jittering. No, I'm not. One thing that I'm going to point out though, is that when I do my leapfrog steps, and you might have noticed, some of you might have noticed this when I had it written down, it's that it kind of looks a little redundant after I've updated Q to take 2 half momentum steps. So actually what we do in practice is we update our momentum, and then we do a bunch of what are Euler steps. So we're just going to do full steps proposing our state and our momentum, unless we've actually exhausted all of our leapfrog steps that we're going to do, because in that case, what we do is we do a half step to finish it off. So this is something like, I can share my code too, and I'm not going to spend too much more time just talking about that. But if you actually go back and you look at the leapfrog algorithm, then this is something that you can do. And miraculously, it works so much better than Euler's method. So here is with that first half step and that last half step. So here is a 2-dimensional example, and I'm going to do 10,000 iterations of both HMC and random walk Metropolis, and then I'm going to plot the traces, and we want them to look like the furry caterpillar. So there we go. I've done 10,000 iterations of each. and I'm plotting both trace plots. In black, I have the random walk metropolis algorithm, and then in red, I have HMC. And if we just look at these traces, then we see that actually the random walk metropolis algorithm is outperforming HMC. So black looks better than red. And then, yes.
In practice, if you have a frequentist analog, do people use the frequentist estimates as initial values?
Yes, they do. That's good practice if you have it, if you can. If I look at the effective sample size of my two methods, so first I look at the effective sample size, and now I'm highlighting it actually in the console. If I look at the effective sample size of my random walk metropolis results, then I have about 1,300 samples in both dimensions, independent samples. And then if I look at my HMC, then I only have 30 independent samples. So looking at the trace plot and looking at the effective sample size, yes, random walk metropolis crushes HMC. And is everybody familiar, by the way, with effective sample size? Okay. So now what I'm going to do is I'm actually going to change my step size for HMC. So my step size was 0.01. And now I'm going to increase it to 0.1. So I'm going to multiply my step size by a factor of 10. And I'm going to do the exact same thing now. 10,000 iterations, done. Okay, so now HMC actually looks a lot better. All I had to do was change my step size. And here I'm doing L equals 20. So I'm doing 20 leapfrog iterations. I can do the exact same thing again, except now I'm going to use a step size of 1. So I'm going to increase it by 10 again. And it's impossible to even see the random walk metropolis trace. So what I'm going to do is I'm actually going to switch colors. So random walk metropolis is now going to be in the foreground and is going to be red. And you can see that actually HMC in the background is doing a better job. Well, one, it looks more and more like a fuzzy caterpillar than the random walk metropolis trace, but also that we're actually doing a little bit better of a job exploring the tails of the target distribution. And then if we want to actually see, to get another statistic beside the fuzzy caterpillar, which I believe is a very technical criterion, then we can look at the effective sample size of both. So again, this is out of 10,000 iterations. Random walk metropolis is, again, it's around 1,300, 1,400 effective samples. And then HMC is actually almost 30,000 independent samples.
Can you remind me how the effective sample size is calculated?
Yeah, that's the question, right? Because that's bizarre and it should be wrong.
Right.
So what we're going to do is we're going to look at the number of samples that we collect. And then we're going to divide by our autocorrelation. So if you want to see what's going on, then we need to actually plot the autocorrelation. So I'm just going to do ACF. And then I'm going to do HMC results. Let's see here. Actually, to make it visible, I'm just going to do HMC results 1. So this is the first dimension. So what this is telling us is that after when I take a single discrete step forward in time, my autocorrelation becomes negative. And that's why you're getting this, what should be like a spurious kind of result, right? When you say that, you know, we've actually managed to collect more effective samples, more independent samples than there are iterations in my Markov chain. This is just what HMC does on this kind of simple toy problem. It gets a negative autocorrelation. What we can also do is we can increase the dimensionality to kind of start to see the strength of HMC. So now we're looking at a 100-dimensional target. And note that it's going just a little bit slower. A little bit slower. So first thing is that I need to tell you is that when I've written, so my random walk metropolis code, I'm actually using the optimal scaling. So the standard deviation is 2.38 or maybe I just have it 2.4 divided by the square root of the dimensionality. So this is as good as we're going to be able to do with the Metropolis Hastings algorithm, which I'm showing you in red, but HMC is actually doing very well. And as a matter of fact, if we look at the effective sample size, again, HMC is still getting that negative autocorrelation. So again, we have a very large number of estimated independent samples. So the minimum here is 25,000. Again, this is from 10,000 iterations of MCMC. I mean, in comparison, the maximum for the random walk metropolis algorithm, I'm highlighting it right here, it's 60. Okay, finally, well, surely there must be a limit to this sort of thing. Let's look at D is equal to 1,000. Everything is now, you can kind of see that it's a little bit slower. Actually, it's taking a while to actually compute the effective sample sizes because there's so many dimensions that we need to compute across. But the maximum performance for random walk metropolis is now 23. And then the minimum is actually, this, I didn't notice this before, but the minimum is 23,000 effective samples from HMC. So we have a 1,000-fold increase. Of course, it's a little bit weird to be talking about that kind of number for 10,000 iterations. But then on the right-hand side, again, you look at the trace plot. The trace looks wonderful for HMC in black. And then in the foreground, you have the random walk metropolis algorithm just kind of doing its thing, but not in a real hurry. So yeah, I think that this is impressive, but the first thing that I wanted to show you is that, it does depend on the tuning, the way that you tune the parameters. And then the other thing that you should bear in mind is that, this is precisely what HMC is supposed to be good at, a log concave target distribution. So yes, these are amazing results, and results like these hold in practice very often, but then they also this algorithm can also be broken very often as well.